Welcome to The Tech Between Us, brought to you by Mouser Electronics, where we help empower innovation together. I'm Raymond Yin, Director of Technical Content at Mouser. In each episode, we'll have a different technology conversation between our tech experts, technical representatives from our manufacturer partners, prominent academics, and industry thought leaders. In this episode, we're talking with Steven Shackell, Product Line Manager for Silicon Carbide and Gallium Nitride products at On Semiconductor, about the evolution in power management components and how to increase system efficiency while decreasing overall system cost. It should be obvious that anything electronic needs a source of power, whether it's line power, battery power, or even an alternate energy source such as solar. With the increased electrification of the world, this need for efficient power is ever increasing and is being compounded by new technologies such as electric vehicles, high-density power supplies for data centers, and solar inverters. Unfortunately, traditional silicon is rapidly reaching the limits of its capabilities to address these new requirements in high voltage and high-density applications. A new class of material is needed to effectively push the boundary of power conversion. Enter the wideband gap semiconductor. So, Steven, welcome to the Tech Between Us. Can you briefly describe what makes a semiconductor wide bandgap, and how is that different from traditional silicon semiconductor materials?
Yeah, so the wide bandgap is more in reference to the energy bandgap between the valence and conduction bands of a semiconductor. So really what this means is it's the amount of energy needed to knock an electron loose from the outer shell so it can move freely inside of the material. The main difference between a wide bandgap device like silicon carbide and GaN is that energy is around 3.3, 3.4 electron volts, to where in silicon, that's around 1.1 electron volts. So 3x that value of silicon versus silicon carbide and GaN. Then because of that property, it gives the device a lot more benefits, such as 10 times higher dielectric breakdown, field strength. This means that smaller thickness can be used for the device, reducing resistance, thus reducing the power losses. The second benefit is of the electron saturation velocity is about 2 times faster in silicon carbide devices. Faster electrons means faster switching. And then we go to the third benefit of the wide bandgap device, and that's the higher energy that's needed to knock those electrons free means that it has lower leakage currents at the elevated temperatures, meaning that theoretically these devices can operate at 250 degrees C and even higher, to where silicon is really limited at about 150 degrees C. What's causing that to actually not be the case in what you see in silicon carbide data sheets is really the mold compound that is used in the packages themselves. And then lastly is the thermal conductivity is 3 times higher. That means the heat that the part generates can get out of the device a lot quicker and into the overall system.
So there are actually quite a few differences between the wide bandgap or silicon carbide and silicon, and it sounds like a lot of advantages. Are there any disadvantages of silicon carbide over silicon?
It's hard to say a disadvantage. It's changing how you do current designs is what I would almost say the disadvantage is it takes a completely different thought process of how to get all the benefits of silicon carbide out of the device. You just can't simply drop in the silicon carbide device and think that you're going to get all those benefits inherently. You really need to completely redesign your system to get all those benefits.
What are the current devices that engineers are able to design with today, and what value do those devices provide over their silicon counterparts?
Just backing up a little bit, right? Silicon carbide diodes were the first sort of mass market wide bandgap device out there. Those have been readily available in the market for a good amount of years already. And that's where people were really using those in power supplies, specifically in the power factor corrector circuit, to just get that immediate boost in efficiency just by switching out a diode. Moving today, there's a lot of development and releasing of silicon carbide MOSFETs. Those voltages range from 650 volts up to 1700 volts and even getting higher as we continue down the development path there. And that's really the heart of most design activity today is with the silicon carbide MOSFETs. And then there are some developments in GaN and some products released there, but that's really still in the infancy stage of a product development cycle.
So with these silicon carbide diodes and MOSFETs, are they going to be drop-in replacements, similar packages to their silicon counterparts, or are you guys looking at something completely different for packaging on these new devices?
Yeah, so from the packaging side of things, the traditional IGBT types of packages are in your TO247 3-lead, 4-lead even. But these packages have some pretty long leads attached to them, right? Those long leads lead to inductances, which when you're talking about these higher switching speeds is not too ideal for a silicon carbide MOSFET where you want to operate maybe at that 80 kilohertz. So we're looking to still release those standard types of power packages, but then moving more into surface mount QFN style of packages, like a QFN 8x8 style of package that gets rid of these long lead inductances, improves the performance of the devices.
Are your customers really embracing this new technology?
Yeah, I mean, everyone's super excited for it. Their view is, or what we see is, it's enabling them to really differentiate themselves from their competitors and providing some very innovative solutions to the market. So customers that are taking and embracing silicon carbide are really starting to set themselves apart from their competitors that are still using traditional silicon devices. And that's getting better system efficiencies, getting reduced sizes. They're seeing it as it's a great way for them to differentiate. Everyone is quite excited when they actually get their hands on the devices.
Yeah, we're seeing the same thing on our side. Customers are definitely asking for these new components and actively searching them out and actively designing with them. So where would you say the sweet spot is for silicon carbide in terms of voltage and power rating? Is there a area that it really is shining?
That area is really going to be, and how I look at it, is more on the voltage side of things, because the power range is, these are all for really, higher power applications. But the voltage range is really 650 volts to 1200 volts. That's the true sweet spot. There are, developments and products released out for 1700 volts and even getting up to 2.3 kilovolts. But really the true sweet spot for silicon carbide is 650 to 1200. For gallium nitride types of devices, that's really going to be, they're going to peak out at about 650 volts and go down to maybe 100 volt realm is where that sort of that cross between silicon carbide and GaN, you can draw that line at 650 volt.
So really for silicon carbides, 600, I know that you guys have just recently released a 900 volt MOSFET. So from there all the way up to 1200, and like you were saying, even 1700, 2100, 2300 volts on up.
Yeah, it's
okay.
A lot of different voltage nodes that we can have, but and it's dependent on each application as well.
So ON is really pushing the envelope for silicon carbide, products and usage. How high do you think it could eventually go?
As far as voltages, there's, can get up to 3.3. You can even get higher. Those markets start becoming a little bit more specialized.
Right.
Where we really want to focus on is in that the 650 volt to probably up to 2.3 kilovolt realm. That's what we want to focus on. And the other area that we want to continue sort of pushing the envelope is putting these silicon carbide MOSFETs inside and diodes inside of modules. There we can really optimize the topologies and really get all the best that we can get out of silicon carbide, both electrically and thermally.
So in these modules, how many devices are you guys looking to put in one of these modules? Is it 2, 4?
It can be 2. You can do a half bridge. You can do a full bridge. We have even more sophisticated modules, say, such as a T-type NPC inverter. So that's upwards of 8, 10 devices of just the actual devices, and then we'll probably have some in parallel with each other as well. So quite a few dies that we can fit inside these modules.
Yeah, I know. I mean, IGBTs have been used in modules for years, and sound like silicon carbide is kind of following that same path.
Yep, definitely is following that same path, and that's really where we think that we can get the best out of silicon carbide, as inductances and things like that are key things that need to be taken care of, and we can specialize the modules and design those modules to have the shortest inductance pass.
What sorts of applications are you guys seeing for just the individual discrete silicon carbide components?
First off was, as I mentioned before, was the power supplies using silicon carbide diodes and PFC stages. That market's sort of been established now. The big market that ramped up starting a few years ago was the solar inverter market. There, that been a huge user of IGBTs and just dominated by IGBTs. But today, you look at most new designs, and they're almost purely using silicon carbide in the solar inverter market. So that's really, from an industrial standpoint, what got the market moving to adopting silicon carbide. Now, following on to that is some EV charging stations, the fast ones that you can charge your car in 30 minutes and less, are predominantly using silicon carbide, and then also UPS systems as well. And then from the automotive side of things, we already know that the biggest supplier of electric vehicles is using silicon carbide in their traction inverter. Today, a lot of other car manufacturers are working with silicon carbide for their new designs as well. So that market is already pretty large, but in the future is going to be growing rapidly.
Right. Yeah, Mouser is a big sponsor of the Formula E circuit, and I know within those Formula E cars, over the last few years, they have pretty much switched exclusively to silicon carbide in the inverters, and saving quite a bit of weight and getting quite a bit of efficiency gains out of their power systems.
Yep. We On Semiconductor, we're also involved with Formula E, partnered with Mercedes there, providing them the traction inverter for their vehicle.
So yeah, it sounds like we're actually competitors, because I think we're sponsoring the Dragon team.
Okay. Should be using our silicon carbide then.
Yeah, yeah, you never know. But yeah, I've read, with small increases in switching speed, I mean, some significant, 10%, 15% gains in power, as well as, significant, 40% reduction in weight. And so there's just a lot of advantages going to silicon carbide in those traction inverters, it seems.
Yeah, I mean, and another one of the benefits is you hit some of them, right? You can reduce the weight.
Right.
What that ultimately does is it extends the vehicle's range, which that's the most marketable aspect of that car manufacturers are looking for is, can you get to that 300 mile per charge? Can you get to that 350 mile per charge? That's what's really going to make a consumer decide what EV they go with. So getting those extra 25 miles is crucial, and silicon carbide allows you to do that.
Yeah, I think it's going to be key in getting there. And, and then on the infrastructure side, like you mentioned, silicon carbide, I know, is a key component of the level 3 chargers that are starting to be deployed out there, the fast chargers.
Yeah, that's the market that we see silicon carbide. It's really going to explode here in the next couple years, especially as governments start putting some more stimulus and investments in infrastructure. One of those key areas is going to be EV charging stations. So that's going to definitely amplify the need and demand on silicon carbide there.
Have you seen any applications that surprised you? I mean, that just kind of came out of left field?
It's hard to identify a true application. We're seeing the use cases range all over the place, from medical to, welding. Everyone's trying to find how they can get the benefit out of silicon carbide. So anywhere where an engineer was using IGBTs, they're starting to look at silicon carbide.
And it sounds like they really should be looking at silicon carbide.
Yes. But my view is, if you're not looking at silicon carbide, then you're falling behind the curve.
Now we'll take a break from today's discussion to acknowledge our partner, On Semiconductor. As a leader in energy-efficient power management devices, On Semiconductor's comprehensive portfolio offers a wide range of components, including 650, 1200, and 1700-volt silicon carbide diodes, and 650, 900, and 1200-volt silicon carbide MOSFETs to suit dozens of applications. To view videos, read articles, and learn more about the latest product introductions from On Semiconductor, visit their content stream on Mouser.com. Click on the link in the description. Let's get back to our conversation with Steven. So we touched on this a little earlier, but in a perfect world, to take full advantage of the new technologies, engineers could simply, once again, in a perfect world, engineers could simply remove their silicon diodes and silicon MOSFETs and IGBTs from their current designs, pop in the silicon carbide devices, seal up their products, and voila, instant efficiency gains, better thermals, higher voltages. Unfortunately, it doesn't quite work like that.
Yeah, I wish it worked like that. We would be selling a lot more already. But
right. So how should design engineers approach working with silicon carbide?
Yeah, I mean, the first step I view it as you need to know how silicon carbide, what benefits you can get from them in your application. Once you understand that, then you know what sort of areas you need to be using silicon carbide in. And then you need to rethink everything in your power stage and sort of start from scratch to get all the benefits out of silicon carbide. If you're just trying to, I'm going to put this in there, I might change my gate drive a little bit, or I might slightly increase my switching speed, you're not going to get all of those benefits out of silicon carbide. It really takes a complete redesign to get those benefits.
So when you say complete redesign, I mean, so we should be completely start from literally from a blank, a blank schematic and start there, or are there other design considerations that can transfer over from designs with silicon?
Yeah, I mean, you're not starting from completely blank piece of paper, right? A lot of your, surrounding components, current sense, and things like that and control can somewhat stay the same. But you most likely need to start thinking about, do I need to change my topologies? I'm using just a standard boost. Do I need to go to more of a active bridge? Things like that you need to think about changing topologies. And then when you're doing that and you're increasing your switching speeds, all of your passive components need to change as well to be tuned for those faster switching speeds. So it's not a full from scratch. You can port over a lot of your knowledge and understanding of power topologies, but you do need to go back a little bit further than just replacing the device.
You've talked about switching speeds. I know IGBTs traditionally in the 20 kilohertz range. What sort of switching speeds are you seeing from silicon carbide devices?
Yeah, I mean, there you can push up to 60, 80 kilohertz. Some are pushing maybe a little even faster. I would say 60 to 80 kilohertz is the key area.
What sort of reduction in the size of your passives and board space could an engineer see from pushing it from a 20 kilohertz IGBT design to an 80 kilohertz silicon carbide design?
Yeah, so you can see about a 75% reduction in the inductor and capacitor values. So that's a pretty large reduction.
That is.
Then that translates directly to dollars, right? So if you look at the cost of the inductors and capacitors in a 20 kilohertz silicon IGBT solar inverter, about 30 kilowatts, you'll see that you can save about $180 in the cost in the inductors and capacitors if you switch that design over to an 80 kilohertz silicon carbide design. You then look at, okay, save $180 in the passives. What's the difference in the cost of the MOSFETs? There's about $160 difference. So you're still coming out a little bit ahead moving over to silicon carbide, which I'd say about $20. And that's not even adding in the fact that your metal usage is going to get drastically reduced as the size is smaller. You can use a smaller heat sink. So there's even other benefits that haven't even been included within that quick calculation.
Right. So you're actually getting better efficiency, you're saving money, you get better thermals out of the overall design. So really, engineers really should be looking at this rather than from a MOSFET to MOSFET or an IGBT to MOSFET direct comparison, looking at the overall system cost and overall system design from one to the other.
Yeah, definitely. If you're just trying to do an apples to apples of an IGBT to a SiC MOSFET, of course the IGBT will always be cheaper. But you looking at the complete solution cost is really where silicon carbide starts leaping ahead of IGBT solutions.
I mean, silicon carbide, especially on the MOSFETs, like you'd mentioned, the diodes have been around for a little while, but the MOSFETs are still relatively new. So they're still kind of in that, almost a startup sort of mode. Engineers can already see a price reduction by using this new technology.
Yeah, definitely, right? As manufacturing ramps up, as there's a transition between 4-inch to 6-inch to 8-inch wafers, there's step function cost reductions for the path for silicon carbide, to where if you look at IGBTs, they've been around for a very long time. That cost roadmap is starting to reach that asymptote.
So starting to plateau off.
Yes. So from a silicon carbide perspective, there's still a lot of room for productivity over the next few years, many years.
That's terrific. What has been your customers' experience in designing with these new silicon carbide devices?
Yeah, I mean, so from their experience, from what we've heard from them, is there is a little bit of a learning curve, a lot of work that needs to go up front. But overall, once they get their hands on the devices and start testing with them, they're seeing great performance. And there is a good amount of communication that needs to occur between ourselves and the customers to make sure that any issues that do arise, we can solve them together. And for the most part, that has been possible to do.
That's terrific. I know with any new technology, I mean, there is a significant learning curve. And you had mentioned testing. What sort of tools are you guys providing engineers for the new devices in terms of simulation and whatnot?
Yeah, so from our simulation perspective, we've really tried to differentiate ourselves with what we call physical scalable models. So these are models that are based on the physical properties of the devices and can model the devices very accurately over all the different characteristics, temperature, what have you. And what you model and see in the simulation is almost exactly matching what you see in real life. So much so that we can really provide a data sheet before we even manufacture the device based off of the models and guarantee that. That's how confident we are in these types of models. So these are available for all of our silicon carbide devices.
So from a customer perspective, they're able to get a model that is extremely accurate over temperature, over a wide voltage range, and they're able to get accurate, real world results rather than just the theoretical results that a lot of models are currently using.
Yeah, it's just not even your sort of DC state. Even looking at the AC characteristics, we can model those very accurately.
That's terrific. Once again, I mean, with any new device, I mean, that's going to be key in, getting customers comfortable working with the new technology and being able to easily design it in to their new devices and increase the adoption rate.
Definitely.
So, Steven, what's next for On Semiconductor and wide bandgap materials and devices? What are you guys working on?
Yeah, so I mean, for our next steps, we're just going to continue building out our portfolios in both discretes and power modules. Our key area of focus there is going to be really on the automotive market, industrial, and the cloud power markets. So that's just continually building out those portfolios, releasing new voltage nodes, creating new next generation types of devices. We're also working on some very exciting wide bandgap activities. So with some very interesting ideas in the pipeline. So definitely stay tuned to On in terms of what we're doing with wide bandgap.
That is great to hear. I mean, these are still kind of in the lab right now, but there's a whole new class of materials. I mean, I guess they're being called ultra wide bandgap. Things like, aluminum gallium nitride, cubic boron nitride, even diamond. Are you guys heading in, even looking at anything like that?
Yeah, definitely looking into diamond. I mean, I'm looking for a lead customer that's willing to pay for it. But so if you know anyone that's looking for a diamond MOSFET, another sort of venture that I'm sort of looking at is going into the jewelry industry, trying to do a diamond MOSFET engagement rings for all those engineers.
All right. So if we find anybody that's looking for that diamond in the rough MOSFET, we'll send them your way.
Definitely.
Sounds good. Thank you for listening to this episode of The Tech Between Us. We've been talking to Steven Shackell of On Semiconductor about the latest advancements in wide bandgap technology. In our next episode, we'll explore the latest applications and future possibilities of artificial intelligence at the edge. Discover more Empowering Innovation Together content at mauser.com/empowering-innovation.